The energy of an electron is more important than its position. So the probability of where the electron is found is given to us through the solutions of the wave function using the Schrödinger equation. By solving this, it gives us information about the size, the shape, and the orientation in space of our orbitals. And these come from the solutions to our Schrödinger equation. So the integer values that are predicted by the Schrödinger equation are what we call quantum numbers. So the first one we've already seen a little bit about. That is our principal quantum number. It is represented by n. So we saw this when we were looking at the Bohr model of the atom, where the different values of n, n1, n2, n3, would give us different wavelengths of light. So this number gives us information about the size and the energy of our orbital, how far we are away from the nucleus. The angular momentum quantum number gives us information, and this is a lowercase l. I know it's a little challenging in some fonts, but the angular momentum quantum number, lowercase l, this gives us information about the shape of the orbital. And the magnetic quantum number, which is m sub l, this gives us information about the orientation in space. And the combination of these three quantum numbers are like an address for our electron inside the atom. So our quantum numbers, we said, are the principal quantum number, and it has possible values of 1 to infinity. So 1 would be closest to the nucleus. Infinity would be when that electron leaves that atom completely. So this is the size and energy of our orbital. Our angular momentum, which is a lowercase l, has possible values of 0, 1, and 2, all the way up to n minus 1. So it is dependent on the principal quantum number as to the possible values that L can be. This gives us information about the shape of the orbital, and we'll look at this in just a minute. The magnetic quantum number, m sub L, it has possible values and is dependent on the angular momentum number from negative L, including 0, to positive L. And this tells us the orientation in space. The energies that our electron can inhabit, so the principal quantum number, the gaps in energy are very large when we are close to the nucleus. So we have a very large difference in energy from n equals 1 to n equals 2. As we travel further from the nucleus, those gaps in energy become smaller and smaller. And we will look at this a little bit further when we get to chapter 8 and we start talking about electron configurations. The angular momentum quantum number has values from 0 to n minus 1, so 1 less than our principal quantum number. The principal quantum number is related to the row on the periodic table. So if it's in row 1, it has an n value of 1. If it is in row 2, it has an n value of 2, and so on. The shape, these have values up to n minus 1. So if L is 0, we give it a letter value because we have so many numbers. If it's 0, we call that the s orbital. So sometimes you'll see L with a number value, sometimes you'll see it with a letter value. Please don't let that confuse you. but if it is 0, that it just equates to the s orbital. S orbitals have a spherical shape, and this is related to the first 2 columns on the periodic table. That is related to our s orbital. If L has a value of 1, we call that the p orbital, and that is related to the last 6 columns on the periodic table, and the shape is like 2 balloons tied at the knots. If L is 2, that is the d orbital. The d orbital is where the transition metals are found on the periodic table, so the middle 10 rows of the periodic table, and most of them have shapes like 4 balloons tied at the knot. We do have this one shape that has a toroid, like a donut, around the middle. If L is equal to 3, that is the f orbital. That is the 2 rows that are usually pulled out of the periodic table and put on the bottom. And it looks like most of the orbitals look like 8 balloons tied at the knots. We do have 3 shapes that have these toroids or the donuts around the middle. So the angular quantum number is related to the shape. When we're describing an orbital, we're using a set of quantum numbers to describe it. So it is a n number, an L number, and an m sub L number that describes one orbital, kind of like an address, like the state, the city, and the road that you live on. If the orbitals have the same n value, the same principal quantum number, means that they are in the same energy level. If they have the same n and L, we say that they're in the same sublevel, or sometimes you'll hear it called as the subshell. So if we are in the first energy level, our principal quantum number would be 1. Our angular momentum quantum number would be 0. So we call this the 1s orbital. The 1s orbital only has one orientation in space, one magnetic quantum number, and so this is called the 1s orbital. Remember, these are spherical in shape. For in the second energy level, this would be n equals 2. We have 2 possible values, so we can have an s, and we can have an s orbital, or we can have a p orbital. So it would be 2s or 2p. If you look at the periodic table, the 2s orbital would be the first 2 elements in the second row, and the 2p orbital would be the 6 elements on the far right side of the second row of the periodic table. Because our s orbital can only have one orientation, it is a sphere, so it's a 2s orbital. Our p orbital, however, because our L value is 1, we can have 3 different quantum m sub L numbers. We can have -1, 0, and 1. So this is related to the px, so p along the x-axis, p along the y-axis, and also the p orbital along the z-axis. So 3 different orientations. This is why we can put more electrons into a p orbital. If we move into the third energy level, now we have 3 L values. Remember, it can be from 0 to n minus 1, so we can have 0, 1, or 2 for our L values. This relates to the 3s orbital, which is a sphere, the 3 p orbitals, which there's 3 different orientations, but it looks like balloon with 2 balloons tied at the knots, or we can have a 3d orbital, which has 5 different orientations. So our m sub L can be -2, 1, or sorry, -2, -1, 0, 1, or +2, because our L value is 2. So anything from -L to +L. 5 different orientations, and these orbitals look like 4 balloons tied at the knots. And again, these are ways that we describe our location of the electrons in the atom. So let's look at an example. Let's describe the orbitals in the 4th energy level and decide how many orbitals exist. So when n equals 4, we have 4 different. When n equals 4, we're in the 4th energy level. So the 4th row of the periodic table, our angular momentum value, we can have anywhere from 0 to n-1. So it can be 0, it could be 1, it could be 2, or it could be 3. Okay? So from 0 to n-1 are the possible values for L. Our m sub L, the magnetic quantum number, can be from -L, including 0, to +L. So if we have L value of 0, this, remember, is equal to the s orbital. So because we're in the 4th energy level, this would be the 4s orbital. Okay. Because our value is 0, our m sub L value can only be equal to 0. So in this case, we have 1 orbital, and it would be the 4s orbital. When L is equal to 1, and because we're in the 4th energy level, this would be the 4p orbital. Our m sub L values can be from -L to +L, including 0. So we can have a -1, a 0, or a 1. There are 3 orbitals. And this we would refer to as the 4p. When L is 2, this is the d orbital. Because we're in the 4th energy level, it's the 4d. Our m sub L possibilities are from -2, because our value is 2, -1, 0, 1, and 2. So we have 5 orbitals possible. And these we would refer to as the 4d orbitals. 5 different orientations in space of the 4d. Finally, if our angular momentum quantum number is 3, this is the f orbital, so 4f. Our m sub L values can be -3, -2, -1, 0, 1, 2, or 3. There are 7 possible orientations. This would be the 4f orbital. So if we add these together, so the number of orbitals is 1 from the s, 3 from the p. I should be adding these. 5 from the d, and 7 from the f. That gives us a total of 16 orbitals, which is 4 squared, or our principal quantum number squared. Okay. So these possible values, these m sub L possible values, and there's one more piece of information that we'll learn at the beginning of chapter 8, but this is part of the reason why the blocks on the periodic table are the length that they are. So the s orbital is 2 blocks long, the p orbital is 6, the d orbital is 10, and the f orbital, or those 2 columns underneath the periodic table, are 14. And that's because of the number of orbitals that are possible in each. So why are atoms spherical? Well, it has to do with the addition of all the different shapes of the orbitals we've talked about. So the s orbitals, which are the lowest energy, the p orbitals, which are a little bit higher energy, then the d and the f. If we add all of those together for each of the energy levels that an atom has, it gives us an overall spherical shape to the atom. And so that's why we typically draw atoms as spheres in our models. As always, there's some suggested problems that you can try at the back of the book to make sure that you understand the concepts that were presented to you in Chapter 7.